differentiation in calculus, undergrad calculus. I assume you've done that as well. Right? I have to start somewhere. I don't want to go back to like fresher, right? I mean, it's supposed to be a graduate course, so I'm compromising to some extent, but I can't compromise too much. Okay, so I assume you know partial differentiation. So so differentiate this partially with respect to time, t, and you will get oh sorry, this one. So you'll get minus I omega out the front times psi, the whole thing, psi. So you get minus I omega psi. Now I can rewrite this. I can put an h bar above and below. So I'll then get minus I h bar omega divided by h bar. So I'm just multiplying above and below by h bar. Doesn't change anything. Times psi, right? But now I've got h bar omega here, right? Which is here. Okay. So this omega now is some kind of frequency of a particle's wave, whatever that means, right? So I can, instead of h bar omega, I can substitute e here. So using this equation, right? So I will get minus I e divided by h bar times psi, and that's what d psi by dt is. Okay. Now similarly, if I take this equation and I differentiate twice by x, by the position, right, I will get ik all squared, so minus k squared psi. And again, the same trick. I multiply above and below by h bar squared. Right? But h bar squared k squared is p squared, right? The momentum of my particle. Okay, so h bar squared k squared equals p squared. So so I can rewrite this minus k squared h bar squared now as p squared. So the second differential with respect to position, x, is equal to minus p squared divided by h bar squared psi. Okay? Alright? Now, we've got this relationship here. This is the energy of the particle, kinetic energy, let's say, which is p squared over 2m. Now, let's, on the right-hand side of both sides here, on the right, let's just put a psi. So E psi will equal p squared divided by 2m psi. That's here, right? Now what can I do? I'm trying to... Where'd this come from? Sorry, I'm not... I think I see. Okay. Again, so we've got p squared divided by 2m times psi. Now, again, divide above and below by h bar squared. It doesn't change anything. So, here and here. Okay. Now, this here, E psi is... I'm skipping steps. Now E psi is equal to what? Oh, from here you've got an E. Yeah, okay. You've got E psi. So take the minus I divided by h. Take that, divide by minus I over h, and bring it. So bring this minus I over h. Bring it over to this side here on the left. So you'll end up with minus h bar divided by I. Yeah, you take this minus I divided by h bar, divide by that, both sides. So you'll get minus h bar over I times d psi by dt. Here it is here, right? And that's what EH equals, because sorry, E psi. E psi. Okay? But E psi equals all this stuff. Right? So, now you've got a minus p squared over h bar squared psi is this, right? So instead of writing this, you can write the second differential. So you substitute that for this, and there it is. And then you can tidy this up a little bit. Multiply by above and below by I. So you'll get minus I h bar divided by I squared. So the two minuses cancel. And so you're just left with this. Right? So this equals that. So you've got an equation now for your wave function in the second differential in terms of the position, x, and the first differential in terms of the time, t. This equation here is the famous Schrödinger equation. And once he derived this, immediately the physics community loved it because it was a wave equation. You know, people were familiar with wave equations because wave equations were part of classical physics for a long time. So this was very popular, and much more popular than the previous so-called matrix mechanics invented by Heisenberg. So Heisenberg was the actual father of the quantum mechanical revolution in the 1920s. But people were unfamiliar with it, and it was obscure and difficult to understand. So when Schrödinger came along, about a year later after Heisenberg, they're all fairly close together in the 20s, middle 20s, came up with this wave equation. Physicists just jumped on it because it was so much more familiar. But it then raised enormous questions about interpretation. Keep coming back to that, right? This is now the formalism, right? Here's an equation in quantum mechanics, but what does it mean? How do you interpret it? This psi function, what is it? What does it represent? What is it in physics that this psi is representing? And look at this. There's a complex number in here. So that whatever solution you get to this equation for your psi, it'll be something of this form roughly. Whatever you get, it's going to involve complex numbers because you've got an I here, a complex number here. So this psi function will be a complex function involving complex numbers. So how can it be physical if that's the case? So the creation of the Schrödinger equation created all kinds of conceptual problems now. People were asking now, screaming for an interpretation. What is this psi function? Is it something physical? Like, is it some physical wave in 3 dimensions in the real world? Something that actually waves? Was it somewhat like de Broglie's idea of a pilot wave? There were pros and cons for that view. As I was saying a bit earlier, Pauli's objection, saying that these waves, like this function here is for just one particle, right? But you get a very similar wave function for a multi-particle system, and then your psi function now is not just in one spatial dimension; it can be in 3n spatial dimensions, where n is the number of particles that you're talking about, and three parameters like x, y, z for each particle. So you can have x1, y1, z1, and then x2, y2, z2, and so forth. So people were puzzled by this, saying, well, this psi function for multi-particle systems seems to exist in a multi-dimensional space, beyond 3 dimensions. So that's puzzling, and it's a complex function because of this I, the square root of -1 in the equation. So you know, it led to a lot of debate. So it's not surprising Solvay, the billionaire, well, I don't know, maybe in those days in the 20s he was a millionaire. Anyway, very rich, and he was interested in science, so he invited all these top people, top quantum mechanics of the planet, mostly European, to come to Brussels to discuss these issues, especially of interpretation. And it was at these conferences where the famous and in some ways bitter debate, one of the greatest scientific debates of the 20th century, between Bohr, Niels Bohr on the one hand, and on the other hand Albert Einstein. These two giant intellects, they were a match for each other. And all his life, Bohr was trying to persuade Einstein that Einstein was wrong, that Einstein's conception that quantum mechanics should be at base deterministic. Bohr just thought that was wrong-headed, just wrong. And Einstein could not persuade Bohr either that quantum mechanics was somehow incomplete, that there should be further variables and new laws appropriately specified that would describe the behavior of a single quantum particle. You know, it would predict you know, deterministically which way it would behave. If you measure that particular one particle, would the result be that value or whatever? That was always Einstein's dream. But and those two never agreed, and Einstein died before in the 50s, unresolved. And even today, there's still, you know, quantum mechanics still takes sides. You know, there are a lot of famous people on the side of Einstein who wanted determinism, and some of the people on that side cynically say, well, there's been no real fundamental progress since the 20s in quantum mechanics. We still don't have like a lower level beyond quantum mechanics, where quantum mechanics would be a kind of upper level approximation of some deeper, lower level, more fundamental level, kind of sub-quantum physics. Doesn't exist. And a lot of other people think that whole notion is just nuts. So it's still very controversial. Well, I've run out of board, and I seem to be getting longer and longer. The next session, I'll start sending these waved particles, like say electrons or photons, through a double slit, the famous double slit experiment, and make you sense the wonder of the properties of these wavicles, because they are truly amazing. And I'll stop there.